Hello fellow students, today we are going to talk about differential equations. So the first thing and the main topic we are going to talk about today is separable differential equations. It is one of the simplest cases for differential equations and it will appear in this form: dy by dx equals some function of x times some function of g. These are called separable ordinary differential equations. They are separable because essentially you can just divide gy to this side and multiply dx to the other side and then separate them into your left hand side full of y and right hand side full of x. And examples of separable ODEs will include dy by dx equals x times y, dy by dx equals 1 over y squared, and dy by dx equals y squared plus 1 or 2x. You can try to identify f of x and g of y. In these cases, they are very easy to identify and you can solve them easily. And to solve a separable ODE is very easy. As I said, we just isolate all the y to one side and x to the other. So if you have your differential equation in this form, you can just divide this g of y to this side and multiply the dx to this side. And now you can see the left hand side is just depend on y and the right hand side just depend on x. So now you can integrate both sides and then get this expression. After integration, you will be essentially finished in solving the problem, just maybe some rearranging to be done. And for the concept of integration c, you only need to add it to one side. In the case, we add it to the x side, as it is the common practice. You can try to think it for yourself why this is the case. When talking about differential equations, it is impossible not to mention physics. As you know, Isaac Newton originally invented calculus just because he wanted to use it to solve physics problems, and then people discovered that calculus is more powerful than geometry for solving problems. And differential equations are one of the most important tools for describing the world around us. They show up literally everywhere, such as population modeling, oscillations, and quantum mechanics. So, examples of separable ODE will include Schrödinger equation. This is the most important equations in quantum mechanics. And this temporal one says the rate of change of the wave function will be proportional to itself. And you can try to solve this ODE by yourself. It's very easy, as you can just treat I, h bar, and e as all constants and just solve for psi of t. And our familiar Newton's second law. Newton originally defined force as the rate of change of the momentum. This you will not solve it easily, as I haven't given you an f of t, but if you are given, you can very easily solve for the momentum. And you have an example in electromagnetism as well. You have Faraday's law. It says the electromotive force in a conductor will be equals to negative time derivative of the magnetic flux. And there's many more examples of differential equations, and they are just a bit harder than separable ones. Now, having talked about how to solve an separable differential equation, let's do a real example. So the question asks us, solve for y if y prime equals 1 plus x plus y squared plus xy squared. So to solve this differential equation, the first thing we're going to notice is that in the original example, y prime will be just equals dy over dx. These two things are just the same. And for the right hand side, we have 1 plus x here. And for the other two terms is y squared plus xy squared. And we can notice that if we take out a common factor of y squared, then you'll be left with another 1 plus x. So now the question is very easy, because you have essentially this is 1 times 1 plus x, and this is a y squared times 1 plus x. So you can take out a common factor of 1 plus x in this case, and you'll be left with 1 plus y squared. And this is all equals to dy by dx. Now you can separate the differential equation, as you can notice this is the function f of x and this is g of y. So now what you are going to do is you divide this 1 over 1 plus y squared to the left hand side and dy, and you multiply the dx to the right hand side. So be 1 plus x times by dx. And now you can just integrate both sides. It's very easy. If you can remember what your integrals, this 1 over 1 plus y squared, its integral will be the inverse tangent of y. So it will be arctan of y. And the right hand side, if you integrate it, you can treat it as a whole, because integral of x and the integral of 1 plus x, they are basically the same. So it will be 1 plus x to the power of 2 divided by 2. So this is just your reverse of a power rule. This is power of 1, you plus 1, get 2, and divide it by the same thing. And don't forget an integration constant of c here. And now you can just solve for y. To cancel out this arctangent, you just take the tangent of both sides. So you get, I will write one more step, tan of arctan of y will be equal to y, and it's the tangent of the right hand side, tangent of 1 plus x all squared divided by 2 plus c. And now this is your solution for y. Now we have another example. It says solve the differential equation of x y squared plus x dx plus y minus x squared y dy equals 0. And this may not seem obvious at the first hand, but it is still a separable differential equation. Why is the case? Because in the first term, you can take out an x, and if you take out x, you have y squared plus 1. Y squared plus 1, and times by dx. And in the second term, you can do basically the same thing, very similar. Take out a common factor of y, and then you have 1 minus x squared dy equals 0. And now you can see it's actually a separable, because this is a function of x, and this is a function of y. This is a function of y, and this is a function of x. They are purely in multiplication relationship, so you can easily separate them. So to solve it, we will first bring this dx term to the right hand side, as we want to have dy and hence y in our left hand side in the final step. So for this term, I want to change it. I will just copy it down, and equals to this thing. If we move it to the right hand side, you have a negative x and y squared plus 1 dx. And now you can separate the variables, move all the x to the right hand side and the y to the left hand side. To do that, it's easy. We just first divide this y squared plus 1 over there. So we have y over y squared plus 1 dy equals to, and we will divide this over the right hand side, negative x and over 1 minus x squared dx. And now what am I going to do is I'm going to multiply both sides of the equation by 2. Why I'm going to do that, you will see in a second. So 2y over y squared plus 1 dy will be equals to 2x. And for the bottom, I will multiply this negative 1 into the denominator. So you basically reverse the sign here. So it will be x squared minus 1 dx. And now maybe you can see it. You can just do a u sub here to integrate, because you have y squared plus 1 in the denominator, and you will notice 2y is exactly the derivative of y squared plus 1. To see it more clearly, we can just do a u sub. If you let u equals y squared plus 1, then du will just be 2y dy. And now you notice exactly this thing here. So your integral will become easy after the u substitution. You have an integral of 2y divided by y squared plus 1 dy. And from the variable substitution, you can see that this thing is basically u at the denominator, so we have 1 over u. And the 2y dy is just du times du. So now the whole thing is very easy. As you can remember, 1 over u is just natural log of u. Now we won't add the absolute value and the constant because it's in the middle process of our differential equation solving. It's not very important now. And you can just substitute the u equals y squared plus 1 in. So it's ln of y squared plus 1. And you can also see why you don't need the absolute value, because y squared plus 1, you know it's a quadratic. It will always be larger than 1. So like the natural log will never, inside it will never be negative. And now back to the differential equation. For this both sides, if you integrate it, the left hand side will be just natural log of y squared plus 1. And the left hand side is very similar. You can see it's just basically the same thing. This is y squared plus 1, this is x squared minus 1, and plus 1 minus 1 doesn't affect anything, because in this step, if you do a u sub again, this plus 1 minus 1 will disappear after the differentiation. So the end product will be just another natural log of x squared minus 1. And another integration constant, c. But now I will not write it as c, I will write it as natural log of c, because it will make our simplification easier. And the constant and the natural log of it is basically another constant, it's the same thing. Now if you remember your log rules, you can see you can multiply the right hand side together. So the left hand side won't change, it's still natural log of y squared plus 1. And the right hand side, you can times this c with this x squared minus 1. So we the natural log of c times x squared minus 1. And now for the last step, it's very easy. You can just basically cancel the natural log on both sides. So the answer will just be y squared plus 1 equals c times x squared minus 1. And now you don't need to write y explicitly on the left hand side, because if you want to do that, you need to take the square root, and it will be a positive and a minus square root, so the answer will look horrible. This form is okay, it's called implicit equation. You can leave your answer in this form. It's not exactly a function, it's a relation, but it's still a solution of a differential equation. And now that's all for the day. See you next time.